Okay, so let's go back over where we were. We were titrating our weak acid with a strong base. The base was in the burette, the weak acid is in the flask. When I first start, just from the very beginning, just like we did here, right? When we started our strong acid, we said, well, what's the pH of the acid in the flask? And in this case, it was 1. Notice that for acetic acid in the flask, the pH is only 2.89 because it's a weaker acid. Then we titrated, did a kind of step from between the beginning and the equivalence point at this half equivalence point. If we go to the half equivalence point, and I'll show you where this is on the graph, we found out using the Henderson-Hasselbalch equation that if these two are equal, which they are here, 0.0025, that the pH is equal to the pKa. And so I realized I forgot to finish that problem. So if I do that, the pH at the half equivalence point for acetic acid and hydroxide is 4.74. This is all making sense. Our pH is going up. We're going up the curve. Then we got to the equivalence point, but we had to do a little bit more calculating because we found that when we got to the equivalence point and pushed it all the way over here, just like when we get to the equivalence point of a strong, correct? We get to the equivalence point of a strong, we're all the way over here. This is 7 because these are neutral. When we do the same thing here, we get this. This goes on to react with water and make a little bit of hydroxide. And so we calculated the pH to be 8.72, which is not 7. All right, let's keep going. Now what we're going to do is we're going to go over a little bit. We're going to go over the equivalence point. Again, we still have the same number of moles of acetic acid, but now we've added a little bit of extra moles of hydroxide. So now we have how many moles excess? 0.001 mole excess. The total volume is 50 plus 51 milliliters, which is 0.101 liters. That means that my molarity is 0.0099, and the pH, I should say pOH is 3, but my pH is 11. So now I've gone all the way from the very beginning, which is acidic, through the halfway equivalence, to the equivalence, and now over the curve. So let's look at what that looks like graphically. Now let's start first at this half equivalence because this is an extra thing. So this black line right here, that's your typical strong acid, strong base. Flat part of the curve, quickly comes up, nice S shape. Now, for weaks, it's going to be slightly different. One, they are going to start at above what you would expect for this equivalent concentration of a strong. So they're going to start a little bit higher. We're also going to get what's called this halfway equivalence. So their equivalence points are over here. That's where the number of moles of acid and base are the same. And if you look at a strong acid, there it is right there. It's at 7. But notice for all the weaks, they're all higher. Now, halfway between here and the equivalence points is this half equivalence point. Now, in this case, if you notice, the Ka of this acid is 10 to the minus 2, so the half equivalence point is 2. We move up to this one. The Ka is 10 to the minus 4. The half equivalence point, the pH is 4. This one, the Ka is 10 to the minus 6. The halfway point between here and the equivalence point is at 6. Do you see the pattern here? Here it's 8. So all of these are showing, right, that the Ka, the pH, at half the equivalence, halfway the distance between where you start and when you're neutralized, or not when you're neutralized, because in the case of weaks, it's not neutral, but at the equivalence point is equal to the pH is equal to the pKa. right? Now, the shape of these curves are going to be slightly different. So here's the shape of a curve of a strong acid, very strong S-shaped curve. For weaks, you're going to get kind of a little bump here. In general, it's going to flatten out for a while, and we're going to talk about what that is. And then you're going to get a slightly, sometimes, in fact, some weak acids, this can be really drawn out. And this steep part of this curve can also be flattened out as well. So they look slightly different. Again, for each, you're going to get an equivalence point, which is going to be here somewhere in the middle of that steep part of the curve. But for acids, you do get this half equivalence, which tells you what the pH is at that point, which can be useful. I can do the same thing. Here's the titration of a strong base and a strong acid. So I'm going down. Now for a weak base, you tend to get sort of a little bump. You get a little dip. That flattens out. Again, we're going to get the half equivalence point here, the equivalence point, and then it's going to flatten out there, right? So again, we can ID the acid. We can titrate it. We could find out what the half equivalence point is, then calculate the Ka, and I could look at a table of Kas, and that helps me figure out what the identity of my acid is, and that could be very useful information, because at this point here, the pH is equal to the pKa. So kind of in summary, I've got my starting point is going to be a little higher than it's going to be with a strong. I have this half equivalence point that I can calculate the Ka from. And then my equivalence point, notice, is going to be slightly higher than 7. Slightly higher than 7 because I make that little bit of hydroxide. So let's go on and summarize. Okay. In a solution of a weak acid, the pH has the initial pH is going to be higher, obviously, because it's not a strong acid. At the halfway point, the pH is going to be equal to the pKa. Near the equivalence point, the rapid rise portion of the curve is smaller. It's not going to be as tall. Sometimes it's even a little bit flattened out. And the pH at the equivalence point is greater than 7. It's not 7 like it is for a strong, right? Because the salt that is produced behaves like a base. And then we're going to see, going the opposite direction, if I have a weak base and I titrate it with a strong acid, my equivalence point is going to be slightly less than 7, because I'm going to make usually an ammonium salt, which is slightly acidic. And so my equivalence point is going to be below 7. Real quick before we go on, we're going to talk a little bit quickly about polyprotics. Again, you don't need to know how to calculate these, but we do need to kind of know theoretically how they work. Remember that for something like this, I've got a series of things happening, don't I? I'm going to lose one of my protons. That's going to look like that. But then that can go on to lose another proton. Plus. And then that can go on to lose another one. Oops. 3 minus, not 3 plus. Sorry about that. All right. Now, in this curve, I've only got 1, 2, 3 species, so it's only detecting a couple of these processes. So what's basically happening at A is I have primarily H3PO4. Then I lose a proton, it goes through here, loses it, goes through the equivalence point, and then I'm up here at HPO4 minus. Sorry, 2 minus. No, minus. H2PO4, 2 minus. And then I do this again. I go here, and I get HPO4 Sorry, that's just 1 minus. That's 2 minus. Sorry about that. Now I've got it right. And then I get HPO42 minus. This is pretty much negligible. Remember, the first one is really the only one that determines in a polyprotic what the pH of the solution is. The second one is minimal. This one is almost non-existent. So we're only looking at these 3 species, but you can see I kind of have these 1 process, 2 process, and off I go. I could do another one and lose that last process. So that's mainly just for you to be able to recognize that a shape, multiple S-shaped curves like this indicate the presence of a polyprotic acid. Now, what we're going to look at next is how we choose the indicators to do these. For your AP test, you need to be able to do that. Now, we know that the pH changes very rapidly at the equivalence point. So what happens is 1 drop of a titrant can change the pH by several units. For that reason, the indicator should work in that rapid rise region. That's the perfect place, because then it will be able to detect that very steep part of the curve and show us where we are. So what we do is we look at our curve and we say, okay, in the case of these, I need an indicator that is going to work effectively in these ranges. So I'm going to show you kind of an example of this. So for the first one, it says, why is methyl red not indicated for the case of titration of acetic acid? So if you look at this, here is that steep part of the curve. Methyl red is going to change down here, and we're done. We're not going to know what happens after that point, and that's the information we're looking for. So we would go with phenolphthalein for this one, because that changes right in that range. By nature, that chemical changes in that range. Similarly, if I look at these 2 curves, let's say I was taking a base and titrating it, it's a weak base, titrating it with a strong acid. What I want is I want one that is going to be working my equivalence point. So with this one, phenolphthalein is not the way to choose for this ammonia one. For this one, I would rather have the methyl red indicator, because it's going to change right near my equivalence point. And so because of that, that is going to be the indicator that I would choose to use. So that's a little bit about pH curves. We're going to be doing a lot of practice. And then next, we're going to incorporate buffers into this and kind of put it all together towards the end of the week for your test on Wednesday.